그 저번 시간에 말씀드렸던 부분을 약간 좀 수정해서 어 뭐랄까 좀 수정을 좀 다시 말씀을 좀 드려야 될 것 같은데 여기 이 그림 혹시 생각이 나시는지 이와 비슷한 그림. 음, 우리 이제 로보트의 카메라 노드가 있고 그다음에 I'm sorry, I'm sorry. This should be in English. Sorry, I'm sorry. So um, this is my third lecture. The first lecture I talked about image detection uh, using YOLO. The second lecture that was last week was about LLMs. And today I'm going to be talking about reinforcement learning or RL. And before I do that, I want to just talk about, or I want to just um, uh, I probably cause some confusion. So I want to sort of modify what I've said so far with regards to the system here. So we as a user, we have a computer, and that's where we have a program, a Python program here. And this program, or this is where we are, is connected to the robot. The robot has a camera node and it also has an action node. Okay, so the camera node sends us image of what the robot sees. Okay, and as a user, based on what what the robot sees, we ask or we uh, provide our objective to the LLM. So we call LLM with the image that the robot sends us and also the task in mind. And this is sent to the LLM, which is in the cloud. Okay. So we're going to be using an LLM that is not residing in the robot, but inside is in the cloud. Uh, you can set it up so that the LLM is residing inside the robot. What I uh, explained last time was a situation where the LLM was in the cloud. So you send your image and prompt to the cloud, and the cloud, in order to achieve the objective that is stated as a prompt, comes back with some instructions. And this instruction is relayed to the robot in the action node. And this action node converts it into actual um, um, executions or actions that would move the motor in the robot. Okay. So here's a picture of the robot with various motors, and we sent this signal called the pulse width modulation. Okay, and this pulse width modulation uh, uh, actuates or moves the angle of the robot. Okay, so if it's zero, then um, so the position. Uh, so we can move the angle with by changing the pulse width. Okay, so each of the motor has is being sent different pulses uh, to direct it with different angle, And then there are various sequences for performing a certain action, like, what is it? Move to the right or move to the left and so forth. Okay. So this is actually this action is pick center, pick center. So it's going through six actions, movements in sequence. There's different durations and different uh, uh, pulse width modulation for different motors to do a, uh, to perform the peak center. Okay. And to execute this complex task, user records sequence of motor positions into an action group. Okay, so this is the action group, and is the so this robot is high uh, wonder, and it's high wonder's independent file format for saving this action. Okay, this is where it's set. So, for instance, set motor 1 through 6 with the position values 8, 7, 5, 650, 15, and so forth for iteration of 0.5 seconds. Okay, that's information. And you can set this primitive action or group action group, pick center, uh, by using teleoperation. Okay, so you use your mouse to make this to um, move the motor. Okay, to see that you are actually performing that action. Pick center. Okay, so you use your mouse and you can find out what the pulse width is for each of the motor as you are uh, performing pick center with the mouse, and it will record all of this. Okay, and then once you've performed this uh, peak center, okay, uh, uh, it will be stored in the file called D6A. Okay, and this is so you go if you run this thing, it would run this sequence. So when you're instructing the LLM, you have to. So these are the primitive or action groups: turn, pick, and place, and move. So this is so this is just an example. There's 4 that have been defined, and you can define it also. You can also define the direction, left, right, and center, and quantitative values of nothing, 45 and 90, and so forth. So you can call up a particular uh, action group. You can move it in a certain direction by choosing one of these primitives, and then setting the magnitude by, it allows 45 and 90 now. Okay. So this is something that you can do. Okay. And this was pretty much explained. And I went over this thing using LLM, and I sort of gave you a template Python program. Okay. Today, I'm going to be talking about reinforcement learning. And reinforcement learning is an algorithm or a research area or the software that that defines a policy, and a policy is a function given a state. It will generate an appropriate action. Okay, and this is so stochastic, meaning that for a particular state, um, the action is not always fixed, but it's like rolling a dice. So with some probability, it can perform action A, uh, and other probabilities it could, and it could also perform B in other uh, at different time. Okay, so when you are incorporating RL with the robot, this is a situation that you may have. So this looks very different from the LLM, instructing the LLM to perform the action. Here, you have a policy, and it takes states and produces the action. And the way it works is the robot provides the situation, okay, images, its situation. It takes, and we call that the state, and that is, that produces a particular action. Okay. Maybe the action is only 4. Move forward, move backward, move to the left, and move to the right. Okay. So it performs one of the 6 actions. Okay. But yeah, so that's that. And once you have the action, the RL interface, okay, so this action is actually in terms of the change in the robot position change. So it's represented in terms of delta X and delta Y and delta Z. Okay, so where is it now, and where do you want it to move to? And the policy outputs the difference between the X and the Y and the Z coordinates to perform that task. Okay, so that is the policy provides the deltas, okay, from where you are to your objective, and then that delta is converted into a set of instructions, okay, and that is done through the RL interface. Mhm. And this is the picture that you get. Mhm. Now, you can perform RL in an offline manner or online manner. Offline is very simple. You gather data, and then you determine all the parameters, and based on that parameter, you actually execute the action in the real environment. The online case, online RL, the robot performs the action in the robot, and it gets feedback. And we are going to only talk about offline reinforcement learning, and some people might not like it, but offline is safe because it's not online. It's not online. So, and some situations don't allow online RL because online RL, you're gathering data by exploring various actions and getting the reward for that. If that happens with the car, then that can cause a huge problem. But we're going to be talking about offline reinforcement learning. So uh, before it's actually used, it is the data is collected. Okay. So offline, here is an offline reinforcement learning. Pick up the blue cube. Okay. So we're going to run reinforcement learning on the robot to select the best action from the current state. Yeah. And using offline reinforcement learning, we will train the robot on pre-collected data to train which action is taken. And we collect the training data by teleoperating the robot with a keyboard and saving each state action pair into the data set. And collecting data set the collected data is stored in the teleoperation data set or folder, and it's used during training. So here is all the folders and files that are present within the robot. So the particular RL algorithm that is used in this example is IQL. Okay. And the way this works is the blue dots, I don't know if you can see it, collected data. So what you're doing is you're by moving the mouse or moving the keyboard, usually the keyboard, you can collect and save that data, and that will be teleoperated Korean here. Okay. And then whatever is the output is sent to the default data. Okay, so the directory that you see in this slide is in your robot, and it has a lot of direct files, and some of these files represents data collected from the teleoperation. Okay, so here it is. You collect and save data by using your keyboard, and test the data file with play teleoperation data set. So with your mouse, you can move the robot and you can save that sequence, and that will reside in the teleoperation data set. That will be right here. And you can also save the sequence of motor and play that using this play teleoperation data set. Okay. So you can actually move your mouse and have the robot look to the left side and pick up your cube. Okay. And that will be stored in the this teleoperation data. So based on this data that was collected by teleoperation, you could train that using your RL algorithm. And the particular RL algorithm that is used in here is IQL. It stands for Implicit Q Learning Algorithm. Okay. And you can study this, and there are a lot of YouTubes and texts that will describe IQL. It's a very basic algorithm for doing reinforcement learning. Okay. And you can train it and uh, train it to get a model, okay? To get a model for this IQL algorithm, all the parameters are stored here. And you can run this model by this run IQL, which runs the parameter that has been learned from the data that was collected by the teller operation. And it should be noted that when you run it, so the policy is giving the delta values, the change that is required in the change in the positioning of the robot. Okay, that's given as delta, and it needs to be sent over to the jet rover gym, which gives you a sequence of set of actions which moves the robot. Okay. Here's the actual Python program. It's a library for robot environment. You initialize the environment and MDP. Okay. And here is reinforcement learning again. And one, you get image from the camera node of the robot, what the robot sees. And the user gives an action. Based on that action and state, you get your reward. Okay. And that reward is being sent to this robot arm. And here is the program that is to collect data set from teller operation. Okay. And here is a sort of an overview of the offline reinforcement learning. So with teller operation, you have the states and the action, and also the reward for a particular action. And this policy gets this trajectory and tries to maximize the discounted reward. Okay. And here is the offline program, offline RL of IQL. Okay. So here is the library for core IQL. Yeah. So that's it for what I wanted to say. Yeah, it's important that you need to convert the delta values into a sequence of actions, primitive actions, and each of the primitive actions are already defined by the teller operator. Okay. Okay, so that ends. If you have any questions, please ask, or you could post them on the chat board. Any questions? Okay, if there's no questions, we'll stop here. I'd just like to just say that we went through YOLO detection. I also went through the LLM, how to give, how to provide task to the LLM, which is residing in the cloud with your current state as an image, and getting instructions to perform or execute a certain action that was done last lecture. And this year, this lecture, I talked about RL, offline RL. So you collect data. You collect data to learn the policy, and that policy will allow you to map the state with the instruction um, to a particular action. And the action is this process, this requires the policy to be learned. So and the action is in the form of the deltas, and you need to convert that deltas into those primitive action groups. Okay. Okay, and that's performed by the RL interface, by the way. Okay, I stop here. If you have any questions, please. This is so we're done with the lecture. For the rest of the semester, you're going to perform a project, okay? So that when you see a new environment with a task, your robot should be able to perform that task in this new environment. The environment will be a sort of a different setting, okay, that you have to maneuver through. And while you do that, you have to perform certain tasks, like picking up the blue block and moving it to a certain position as you're performing the task. No, uh, you are not required to use IQL. IQL is just a very basic RL algorithm. You can use whatever. Uh, you can use whatever sophisticated algorithms that you can, that you are capable of using. Okay, but I expect that when you use a particular algorithm, you know a little bit of the basics of that algorithm. Okay, I didn't go too much into what RL does. RL has state, action, and reward. Okay, and there's a policy. That policy takes the action and maps it into a particular action to maximize the long-term reward. Yeah, that's what an algorithm does. Okay, and IQL is a particular algorithm that does that offline. Any more questions? If there are none, good luck on your project, and we'll keep a close. We'll monitor your progress closely, and if there's any help that's needed, we'll provide that. Okay. So good luck, and we'll set up a date for you to perform this task and we'll have judge from outside, and also the professors or the lecturers and TAs will be available to judge your performance. Okay. Bye-bye.